Hello, and welcome to this Oracle Machine Learning Office Hours. Today's session is Machine Learning 101, Clustering. My name is Mark Hornick, Senior Director, Product Management, Data Science and Machine Learning, and I'm joined by Marcos Arancibia, Product Manager, Data Science and Big Data. Marcos is our key speaker. Will be telling us all about the things you want to know about clustering, and we'll see a very interesting demo as well on that front. The next session is targeted at October 20th, and that will be Machine Learning 102, Clustering, where we're going to learn more about the various methods on multiple dimensions, how to compare cluster techniques, and explore dimensionality reduction, as well as how to extract only the most meaningful attributes from datasets with a lot of attributes or derived attributes. For more information on Oracle Machine Learning, you can go to our website at oracle.com/machine-learning with a lot of details on the various components that we have with Oracle Machine Learning. In addition, if you'd like to try out Oracle Machine Learning, the SQL interface today with Autonomous Database, you can open a cloud-free tier, and you'll have immediate access to the machine learning algorithms in the database through our OML Notebooks interface. So for today's session again, Marcos, I would turn it over to you. We'll be talking about clustering, Machine Learning 101.
Thank you very much, Mark. Hi, everyone. So welcome to this session. As Mark mentioned, we're going to talk about clustering, right? So if you missed the machine learning session that we went originally, you can go back to the session from May 19, and we have the basics of machine learning back there. So today's idea is to talk about, what is clustering, the algorithms and methods, and then look at the types of data needed for clustering and the terminology, look a little bit of the workflow and the data preparation needed for that, and then check what the data that we're going to be using for an example, and then look at the model intuition. I think that's going to be something that helps you that. And then we're going to go into actually a demo of the machine learning, different machine learning algorithms. So basically, clustering is widely used to try to group things or group people or group machines or group, right? You're always trying to group things, right? You're trying to create groups of things that behave the same way. And that's basically what you're doing. It's typically unsupervised. There are some sort of supervised kind of training that happens. For example, if a human or a person says, I have this group of people and that group of people, and now the machine, you try to group these people by their behavior, and now I can identify them and check with an expert whether my model is okay. But typically that's an unsupervised process, right? So in market research and surveys, this is one of the things that you use when you're trying to create pockets, right, of people and trying to understand their behavior. So like you're trying to interview people or trying to understand behavior down here in Miami, for example, then you don't have to interview everyone, right? You basically try to find the right people that will be representative of a group of people that now you're trying to understand. So there's a lot of different things about the customer behavior as well that you normally try to do. Anomaly detection is also another use case that is very good. Crime analysis, when you're trying to understand the behavior of people in different pockets and areas of the city. And then even social network analysis, which, you're trying to recognize communities of people, right? What kind of groups of people like the same kind of things, or that can also help you with graph, right? With the fraud models, with churn models. Well, there's a lot of different uses, right, that you can do, you can have for that. There are many types of algorithms and methods. If you go to something like Wikipedia, you can see, lots and lots of different families of methods, right? But basically, we have the basic distance-based methods or centroid models. These are like your typical k-means algorithm, right? And that's one of the most classical ones, most used ones, more than 50 years old. So it is it is a very, specific algorithm that we're going to be talking about in an example here. We have grid-based algorithms as well. So those try to create more of a grid on top of the data. And then you have density-based, so those are probably the more modern ones, expectation maximization, the Gaussian mixture models, things along those lines. So basically the k-means method, and I have an animation on the right to show you more or less what it does. Basically, the k-means method, born probably 1956, those ideas there, but the term was coined in 67. So the idea is that guy tried to partition the data into, k clusters, right? Where each record belongs to that cluster, and you actually assign it through a distance, right, process. So the core or the middle of that cloud of points then becomes your what we call centroid, right, the center of that. So that's the resulting space, if you will, right? It's basically Voronoi cells where you're splitting that if you were doing that in 2 dimensions, right? For something like the O cluster or orthogonal partitioning, it's basically a grid-based approach. So Oracle has that O cluster patented since 2002, a method that can do these kind of very specific buckets of things, but you can see that now these are grid, right? So the grid based because these are little squares that you're working on trying to identify the buckets, right, of where the data would be. And then you have the newer methods, the expectation maximization. So it's a density-based algorithm. And the advantage here is because it can look at the data and it does not need the data to be at the same size. So the clusters that it finds can be of different sizes and different dispersions. You can see on the right an example. So on the top, you have the original data like Mickey Mouse kind of ears there. And then you have the k-means clustering, right, which tries to create clusters of the same size, but then it makes it wrong, right? So it guesses incorrectly there. And then the expectation maximization cluster, which gets down, much, much closer to the real process, right? So that's basically what it does. So when you think about clustering, right, what kind of data, right, normally we expect? Well, the input data is typically this, right? So you get historical data, any data set, any data you have comes in, but there's no such a thing as a target like we have seen in classification or regression, right, for that matter. There's no target column. Basically, you're saying, I don't know. I want to look at my data and see if there is a pattern here that I can identify from my customers. So at the next step, then when you're predicting this, basically you're going to get a predicted cluster number, right? So you're going to have also predicted probabilities. We can have prediction details, right, for every customer. But usually the default here, the basic thing is I'm going to now have new data coming in, and I'm going to give that data set or that data point a predicted cluster. I'm telling you that guy is similar to the people on segment number X, right? And the input as before is the same thing, right? You have table columns coming in, you have all of the variables, right? You have one ID, you have the rows, and then basically, you have the output that is your predicted cluster now, or segment as well. You will hear that word used commonly as well, right? So segmentation is also very, very common as the process name, right? So now for the workflow, so basically when you think about it, there's no test, right? So basically what we're doing is we get a trained data and we build a model with it. And then we compute cluster statistics. So we look at the assigned cluster number, and there are several statistics that usually you would compute, like within sum of squares, between sum of squares, total sum of square. We'll see the definitions later when I'm showing you the steps. So the model will ideally check for records that are similar, right? And then they want to try to find records that are similar within a cluster And there are very differences between clusters. So the most distance that the model can put between two clusters, the better, right? That's what the models are doing. And then they're trying to create compact clusters and then have those clusters very separate. So that means these really behave differently, right? For scoring then the data, basically, if you have a test data, we are going to assign the most likely cluster to that record. Now, that happens basically using the probabilities. Now, there is a tree that gets printed typically that you can look at, when you can understand the rules on how to assign, one data or one record to a specific cluster. But basically, you use the probability. So in the back, you're saying, let me check the distance, right, between that new record and then all the previous clusters, right, that were assigned before. We're going to check that really soon. So for data preparation, most clustering algorithms will require some transformation, standardization, normalization, missing value imputation. Some of them require that. This is, again, to illustrate that it's important for you guys to keep in mind that, a simple date might actually mean a lot of different things, right? So just one simple, single number in that record of that customer or of that transaction might mean a lot of different things to your domain knowledge side. So it's very important for you, if you can, to look at those things and say whether it makes sense for you to actually transform that, right, and then use that as input. For the specific data preparation, right, on Oracle Machine Learning, the different algorithms, they perform and require a few different things, right? So for k-means, the automatic data preparation basically normalizes all the numeric values before applying that. And again, that's because, if you guys remember from regression, we were talking about the sensitivity to outliers, right? So the process here is almost the same kind of thing. You have to have an outlier very far away, or if you have a number with a large scale, right, then that number would definitely overshadows all the other numbers. Now, if you normalize all of them between 0 and 1, for example, now the weight of those distances, right, now make more sense for the algorithm, right, to work. And then there is a requirement to replace missing values. So it does replace the missing values automatically for you. On the O cluster, the O cluster algorithm actually bins all the numerical variables. So the attributes are binned so that you can use, the equi width binning and compute all of these bins for these automatically as well. And then the missing values in this case are automatically handled as well, right? And for the expectation maximization, there are some specific processes that happen there. So you get both normalization of the numerical attributes, and then you have a top-end binning transformation on the categorical. So you bin the categorical attributes, and then the missing values are handled automatically. So there are a few special things that the model does as well when using Gaussian distributions versus the Bernoulli distributions. But you got that kind of capability, and you have those options to do so. So we're going to use the same data set we've been using for the last sessions. We've been using classification, and we were using that data set for regression as well, which is the on-time data set, right? The arrival and departure delays of domestic flights. Now, we're going to actually do a little twist on that data set, right? We have been using a sample of 10,000 records, and we were trying to predict arrival delays, and then we were trying to predict whether the flight was going to be delayed or not. And in this case now, we're going to do something smaller. We're going to go with basically looking at only the Chicago airport departures on that 10,000 little sample that I had. And we're only going to look at two columns, right? We're going to do flight distance and departure delay. And the idea here is, again, I want to show you the intuition behind this, right? So for k-means, then, the basic intuition is going to be, there's a first step, which is, say I want to identify two clusters, okay? So what I'm going to do now is step one, I'm going to select those 2 points in the space, right? So assuming k equals 2, I randomly select 2 points in the space, okay? And you might say, hey, but these are, very well located. Well, they're not really, right? They're kind of like in this weird position right now. So, and that happens, right? So you will try to find those things randomly. Now, the second step is I will assign each record to a group or to a cluster that is closest to that initial point. So my initial point, or it's called seed as well, right? So my seeds here are basically just these 2 points. Now I'm going to assign the points the same color of that seed so that I can say, okay, now my first step is saying these guys are now my clusters. Now, they don't seem very reasonable, right? And actually, if you look at it, right, you can easily see that. Probably a better way would have been to select the top part and then the bottom part, right, as a second cluster. But that's basically what the process does. So the first step is assigning everyone to the cluster closest to it. And now that's where the magic happens. So now you move that seed to the middle of that cloud. Let's call it the weight, right? So the weight of that cloud, that's called the centroid. The centroid of the cluster is basically the middle point of all points, right? That's the middle, the average, right, of all the entire points there. Now, because we moved that becomes that estimation of that centroid. And guess what? We do it again. Repeat the process. So now that we moved our centroid, we reassign all the points closest to my centroid. So now this guy that is very far away on the top left here, it actually seems more, in line with the top, right? Again, but that's where the magic continues to happen, because now I repeat the step 2 and 3. So I now assign them to the closest one, and I move my point again to the center of the mass there, right? So now that I move them again, I redo the training again, and I recheck the distances. And now that lonely point on the top, now it's closest to this one. So now that everyone stopped at that point, I keep moving that process, but you can now see, right, intuitively, if you keep moving it to a certain point, you move it and that's it, right? At that point, you're in the middle of that. The other point is in the middle of that. And then there's not going to be any more movement, right? So to a certain level of threshold, basically, when there's no more movement, that means the clusters are stable, right? So that the k-means actually converge to a point where it can tell you, yep, these are the segments that I found, and I'm not moving from here. So at that point is where we decide, okay, that's what the k-means are telling me. And now these 2 points, these 2 final centers of those clouds of points are what we call the centroids, right? That's the basic solution for that. Now, for the centroids now, if you think about a new customer, right? So I have a new customer coming in, right? Or a new flight in this case, right? I have a new flight coming out of Chicago, and the point comes down to that little guy here. So this is a new point. So what cluster is that in? So basically, it's very easy. The new scoring is going to just look at the distance, right? In this case, between that centroid and this centroid and your new point. And because you're closer to this guy is going to turn orange, okay? So basically, that's the at that point is when you're saying, okay, I can score now more points coming in because I only need my centroids to do that scoring. That's basically what the cluster model keeps, right? Is that those centroid points, and of course, lots of other statistics and interesting things, but basically the most crucial is the centroid location so that I can score. Now, when we think about a model then of this kind, you can probably also intuitively think about the kind of thing that you're trying to measure. So there is something very commonly known as the within cluster sum of squares. And that number basically means I'm trying to measure the distance between every point and their own centroid. And if somehow these are closer and smaller, so the smaller this distance is, probably the better the model, right? So when you think about one model comparing to the other, right, or two different types of techniques or models or steps trying to do the same thing, you want to have the smaller total within sum of squares, right? Because that tells you you have more compact clusters. Now, you want to also maximize the distance between the centroids, right? Because that means if I have a very compact cluster and I have a very far away clusters one from each other, that means that my solution is getting better. So that potentially is what we call the between cluster sum of squares. So normally you measure that kind of distance, and then if you have many clusters, you are going to do that for all those clusters, and then sum that big, get that big sum up, right? So you're going to sum that entire process. That's basically the steps on a typical k-means process that you're going to see. And then the properties, right, for k-means in particular, right? When you think about things like I'm trying to identify the ideal number of clusters, right, for k-means. K-means as the method actually requires you to give it the k. So you have to give the model how many clusters you are looking for. There are many times when that is not really possible. There are many times when understand or you don't know, right? If you have thousands and thousands of different customers coming in, you might not know whether there is any groupings there, right? So normally you will try to do that by domain knowledge. There are many times when you try to work with even small groups where you can ask people, interview people, review processes, right? And then you can come up. So there's normally a group of people in the company, a domain knowledge, a product owner that will probably know, right? It's going to have an intuition. He's like, okay, I think there are 5 types of people, right, that come by in our website or something like that. So you will have some intuition initially, but there are a few methods that were created, right? So there are traditional techniques called the elbow method. That's back from the 50s. Then there is a silhouette method from the 80s, and there is the gap statistics from the 2000s. So there are a few of these things that interact and that you could use to try to identify the quality of a model. We're going to see more on that on the 102 session, right, in October. So also an important thing is the initialization of the random seeds, right? So remember that we started with 2 random numbers we put in there in the screen there. But normally the k-means is kind of slow, right, to try to find out the best initialization methods. And it's never like ideal. Sometimes what the problem is, depending on where you put the points, something converges and then you end up stuck with something that is not ideal. So there are a lot of new methods that were developed for that. some call the k-means plus plus. And by the way, the slides are going to have the links to Wikipedia or a paper, right, on these methods. But you can have the k-means plus plus, and then back in 2001, because the k-means plus plus is slow and needs to do k passes through the data, back in 2001, a group of gentlemen created the k-means parallel, basically, or scalable k-means plus plus. And so I'm linking to that paper here, but the Oracle Machine Learning Enhanced K-means uses that k-means parallel to actually build this the model and make it faster. Basically, these are the features of the models, right, of the algorithms. So we have the k-means, right, which is, again, I mentioned, distance-based. The number of cases it can handle, so it can handle basically data sets of any size. The O cluster is probably more appropriate for data sets that have, more than 500 records, right? So it's got to be a little larger than the tiny k-means, which could be very small. But it can handle large tables through active sampling, so that it will do some smart sampling for very, very large data sets. And then expectation maximization also handles data sets of any size. In terms of number of attributes, the O cluster, right, the grid is also going to work better for larger number of attributes. And the k-means is not great at scaling up on that dimensionality. Is going to hit a problem. So you might want to keep it for a lower number of attributes. So don't go crazy with the k-means, and 1,000 attributes is not going to be something that you want to like, right? The answer to that. And then the expectation maximization is one that can handle both, right? It can handle larger number of attributes and smaller. It's good at both things. In terms of number of clusters, the k-means, as I mentioned before, is user specified. So even though the Oracle k-means uses a hierarchical clustering, right? We end up building a hierarchy behind the scenes for that, but we're going to stop on the number of clusters that the user specified, right? That's the specific process there. So the O cluster, on the other hand, is going to do an automatic determination of the number of segments, and the expectation maximization does that as well. So they all work on hierarchical clustering, and they all work with probabilistic cluster assignment, which I mentioned before. So when you have a new record coming in, I can give you the rules, but I'm going to use a probabilistic clustering assignment in there, right, inside that model. So with that, let's take a look at a quick demo of that process. So here we have the Oracle Machine Learning for Python. Again, I'm using the OML for Pi here. And again, as soon as OML for Pi is out, I'll get you guys a copy of this notebook as well. So for basically, what we're going to look at is, well, we have data set that will be used, explore the data, create a subset of that data, build a simple k-means, right? We're going to start with k model equals 2, k equals 2. Create a function for building, scoring, and plotting the k-means, and then test k-means for k from 2 to 7. And then we're going to build an expectation maximization model with an automatic number of clusters. And then we're going to create a function for building and scoring and plotting that and expectation maximization, so that we can test it with an automatic, or also manually telling it how many maximum clusters we want. Okay, because that's one option for it. The data set, as I mentioned before, we're going to use is the on-time data set. We will test only 2 dimensions. So we're going to be playing with departure delay and with distance. Those are the 2 columns we're going to use. So basic initialization of our environment. And then exploring the data again with Python. I think we did that in all the other sessions, right? So that's basically the on-time data set here. And we're going to be looking at, again, at the some of the only two of the columns here, right? We're basically looking at distance and then departure delay, and only for the Chicago O'Hare origin, right? Only for ORD there. So we're going to select that. And also, for good measure, we're going to do an outliers, right? So we're going to filter out some outliers, right, from departure delays here. We're going to filter outliers from distance, right? Because if you're flying less than 200 miles, I would suggest driving, especially nowadays, but I would suggest driving anyway, right? I go to Orlando sometimes, and whenever I needed to go to Orlando, normally I would not, I mean, the flight is like really short flight, 40 minutes or so. But the problem is the time it takes for me to get from my home to the airport, wait for an hour, fly there, and then get a car there in the airport, and then drive, to the customer or to the Oracle office there. It's probably longer than what it takes for me to just drive from my home to the office. So anyway, so I'm cutting down and saying you probably want to fly more than 200 miles, and I was saying less than 2,000 miles. So I'm cutting off also the flights that go maybe to Hawaii. I guess they're larger than this. Again, just to get a small set, right? And then the origin of the flight is Chicago. Of course, the flight cannot have been canceled and cannot have been diverted. I'm just saying, put those flights that actually got to the destination. And then I want to look at distance and departure delay. So visualizing that data with Zeppelin and also with matplotlib, right? So if I want to look at the data, when you look at the distance here and departure delay, we're looking at around 400 or so records. So I got 400 flights here. They are not super clear, right? But you can probably make out one segment over here, maybe another one on top. Maybe there's a little group here, right? So you more or less have that intuition, right? So let's take a look at what the k-means model can do with k equals 2 clusters. So the first step is to build a model. What we do here is we're basically saying the settings, these are the settings for my model. I'm just saying 20 iterations. Remember those iterations we were doing, right? Move the centroid and then get everyone together and then move the centroid again. So what we're saying is, yeah, you can use up to 20 iterations if you need. And then we're giving you a random seed, which is fine. It's just whatever number you want to give it. So now I'm passing 2 clusters plus the settings that I just got. And I'm going to fit that onto the data, right? That data that have 2 columns there. And I'm going to give it the model a name. So when you give the model a name here, basically that tells the Oracle Machine Learning to actually store that model with this specific name in the system, so that you can score not only with the object here, but another user could easily score with that model, because now that model has a name, so you can even score with SQL, right, directly, for example, right? Okay, so now we ran the model, and then this is basically the output. So we get the output of that model, and we can see right here the algorithm name, some of the settings, right? So you see the amount of settings I have here. So basically, the only thing I passed was cluster numbers, right? The number 2 clusters that I wanted, the iterations 20, but I did not touch all the other things, and I could have. So there are many other things that you can. We have in the documentation that you can touch. And you can say, I don't want data preparation, I want to do it myself. Or you can say, I don't want Euclidean distance. So you can select many of these options by yourself, right? Then you get global statistics, the attributes are used, and then the clusters. Now the clusters, remember I asked for 2 clusters, right? So you see 3 numbers here, but it's fine. What it's saying is there's a parent cluster, right? Which was the number 1 there. And then there's these 2 child clusters, right? So that's the second tree level, let's say, right? If you think about a tree, a decision tree. So now the cluster number 2 and cluster number 3 are the ones that actually were the ones that you're going to be using for scoring, right? And then the taxonomy, and then the leaf cluster count. So as I mentioned, cluster number 2 and cluster number 3, you can see how many records, right? You have 289 records of the original 481, I think, and then now 122, right? So, or 411, yeah. So for that, then on the right-hand side, I can check, for example, clusters, right? So if I check clusters, I have now the same data that I have there, right? But just in an easier, nicer way to look at it. Okay. Now what I'm going to do is I'm going to predict. So I'm going to run the prediction, and I have two types of things that I can predict. So I can predict basically the cluster itself, the cluster ID, or I can predict the probabilities of belonging to the cluster, right? And you might want to have both. So depending on what you're doing, right? Depending exactly on what your analysis is, right? But for example, this same kind of process, you can check the cluster ID here, right? For that, and then you can check in this case the probability of that record belonging to cluster number 2 and probability of that record belonging to cluster number 3, for example, right? So those are the things that you can work on when you're looking at the clustering, right? Now, what I would like to do now is then create a chart, right? Create a chart to show that to me. So how that happened. So this is the clustering right now. So this is k-means equals 2. So you can see that because of this border, right, the k-means kind of creates this kind of things that it needs to be almost like, probably the same kind of distance, right? You can imagine the centroids over here. So so basically what I did is I then, for plotting, right, I just pulled the predictions. The k-means model object has something called a score that can give me the total within sum of squares for the model. And then I basically plot, right? So I'm plotting for every group, right? So I'm splitting up that in group by cluster ID, and for every cluster ID, I'm plotting it. So I see cluster number 2, cluster number 3 here, right? Those are the two guys that I had before. And if I wanted to check whether that number that is coming automatically out of the model is correct, I mean, I'm just taking the transform is actually the distance. So I can have the distance between every record and its own centroid. So if I square that distance and then if I sum it all, you get basically that, right? So you get the same number that I was talking about here, right? So that's basically the sum of the square distances between each cluster and its centroids. So they are the total within sum of squares. So let's create a function, right? So what I'm doing here now is I'm creating a function to do it all, right? Because I want to play with the k, right? With the number of clusters, right? So I'm added the k there. First things, remember always to drop the model, right? Because otherwise you might get an error if you're using the model name. And then we're gonna run some basic things. So some basic steps for coloring, cycle the colors between the clusters. So we're doing that. We're then going to build a model here, predict the model, and then pull the predictions locally. Get the model score for the text, right? Get the unique cluster names, right? So you gave me k, I built the models, and now I'm actually picking the correct at the actual number of clusters, right, that I get. And then I'm building just a map of colors, right? Just simple thing. And then I'm then building that. Now this time I will do the as a label here. right? As a label, I'm going to give you the number and not the actual cluster number, just because it's maybe easier for us to understand. So let's take a look. Let's take a look what happens, right? So remember that I was giving you the cluster was 2 and then the cluster was 3. So I just changed that to 0, 1. So it's easy for you to follow when you're building different number of clusters. Otherwise, this guy's going to say 4, 7, 14, and you have no idea what's going on. So again, that's just to help us visualize this, right? So with k equals 2, remember this was the chart we had before, right? So these two separate clusters. When you tell k-means to search for 3 clusters, it finds that kind of weird shape. And again, it's happening because if you guys remember, right, it's trying to find the same size, right? It's trying to find a distribution here that are almost like equally sized, kind of in this 2 dimensions, right? So going to a k equals 4, it seems like it's screwed up completely here because it now is showing something that is not really reasonable, right? So yeah, we probably see that for k-means that 4 cluster would not have worked anyway. And then, just a test for k equals 5, and then 6 and 7, right? So you see that this starts getting, instead of getting more precise, right? And you're thinking, well, they might isolate these guys or isolate these guys. Remember, k-means is looking for the same size. So this is not going to look reasonable, okay? This is not looking great. So for if we're moving for expectation maximization, right, then in the expectation maximization, we have a lot of options for expectation maximization. We can add the settings over here. Basically, when we say there's a default of threshold for building clusters, this is a default iterations, and normally you have that search enabled for models. So, but you look at when I'm building this, I'm not telling it, right? I'm basically not telling it number of clusters, right? I'm just passing it the settings, and these are the settings. So this is not the number of clusters. There's an automatic threshold here, but that's not it. This is not number of clusters. So I'm passing it, and I'm building that model. Now I fit that model, and I'll see the details. So with that model, what comes back is I have all of the settings, as I mentioned before, right? You get all of these settings for expectation maximization, right? And then, search enabled. I have a maximum number of attributes in 2D, the log likelihood improvement, linkage function. So there's a lot of things that you could potentially ask and change. And this is the default. There is a 10 clusters. That is the default number of clusters. But remember that expectation maximization is always searching for number of clusters. So the 10 here actually only means maximum, right? For EM, this is the maximum number of clusters is 10, okay? Okay, now we continue on, and now these are the settings that it computed. So it came out with that. We have the log likelihood, number of clusters 3, right? And then a number of components 8. So now these are this is the output then. So basically what it created was 3 different clusters. Remember again that if this is a parent, right? So that's the tree level there. But then you end up with the taxonomy. So the parent cluster, right? And then you got the finally the centroids, right? So these are the centroids for those clusters and the leaf clusters, right? So basically this is the final set of clusters you have, right? We got 340 records on one cluster, only 21 records on the other, and 50 records on the third cluster. And the expectation maximization also gives you an attribute importance, right? What is the importance of each attribute? Because we're using only 2 dimensions, then it makes sense that both attributes have the same importance. We're going to see on the 102 class, when we use more attributes that are coming in, the kind of ability of this model to say, well, we found some variables that do not help in any ways, right? So with less importance. And then we have the different points of, say, histograms of that, and then the rules, right, for the clusters. So basically, at what point you decided on one cluster versus the other. Now remember, these rules are not exactly being used for the scoring, because these rules will be a square, right? Like a decision tree will be something very square, while the clustering assignments will be more natural, because they're looking at distributions, right? Density. So for scoring that, we can do the predict again, and then we can see the cluster ID for now our predictions. And if you wanted to look at what the object, right, what of these EM mod object in Python can do, you can just use an __dict __. It will show you all the different things it can do, right? And basically are the things on the left, but you can see their names, the physical names inside, so that you can call them by name. And if you need, at some point to call one of these options or one of these arguments, right, you could call it by name, right? Definitely easy. So let's create a function for building scoring and plotting, right? So the same thing again, but this time instead of inputting a k, I'm going to let it input the entire settings, because I want to play with those settings. I might want to do something different than the normal. So again, same as always, dropping the models if I already have it. And here I'm building, right? I'm creating an EM object with those settings that are coming in from the function, right? Then I fit that to my data that is coming also from the function. I give it a model name just because temporarily I didn't have to. And then I'm going to run the prediction, going to do a pull that locally. And now remember that assignation, right? So I can do pull from the model as a global statistic. I want to pull the log likelihood, specifically that value. And then when I do that, I can store that value, and then I can put it on a chart. That's what I'm doing. So I'm pushing that to a place in the chart. And then same thing again, getting the unique names of the clusters, and then creating a chart with the, with the graph. Same exact thing, right? So let's try with k from automatic, right? And then k equals 2 to k equals 7. So the first thing I run, I do not tell it to use any number of clusters, and it comes back to 3. And this is already looking better, right? Even though I do have some over here that might have been probably part of the one below, but visually you can see that the type of cluster, right? Even it's stretched out, because think about a Gaussian, right? So you're looking at Gaussians here. So you will be looking at the different shapes, right, that you can create. So those 3 clusters probably makes sense, right? Now, if I force it and I say, you know what, I would like a maximum number of clusters of 2, this is what it comes back with, which, again, I think it's probably more reasonable than the k-means. Remember, the k-means came with this cut, right? K-means was cutting it all the way down here because k-means needed that distance to be the same, right? Or to be equidistant. But this guy is saying, no, that makes more sense. You might have a group here and a group down here, right? If you were forcing me to choose 2. If you force it to grab 3, of course, it's going to get the same as the one on top. Now, because it depends, right, on the settings, if you say maximum cluster 4, it's still going to give you 3 in this case. So with the same settings, it's going to still say, you know what? I could not find a 4-cluster model that is better than what I have here. Same thing is going to happen then forward, but now I'm going to force it. So I say, you know what? Increase the number of iterations to 150 and disable the model search. And I can start playing with this thing. So now I'm forcing it to try to find 4 clusters for me, right? And the same thing happens when I jump to 5, even with 200 iterations, it still says, you know, I cannot find a 5th cluster in this place for you. These 4 are the best ones for that setting. So I can keep increasing it and forcing it. So now I'm saying, oh, no, I really want to find 6. So yeah, it went a little too far. You can see that now, because I forced its hand, it's trying to come up with 6, but this doesn't even make sense, right? And then the same thing is going to happen with 7 here. It says, even with 7, it says, no, it's 6, but those 6 are really bad. So, you know, it's something that you probably don't want to try to do, right? You don't want to keep forcing it. So the basic information that we might want to take from this is try to use the default settings if possible and evaluate them and look at the quality. And only touch all of these settings if you really know what you're doing or what you're after, because you might end up with something that you don't necessarily would like, right? Okay, so having said that, so as always, for more information on Oracle Machine Learning, you can always go to oracle.com/machine learning and Q&A. So Mark, I see a lot of activity in the in the question and answers.
Yeah, there were a number, and got to some of them, but there are a few others that we can probably handle live. So let's start with the first one from Erica. If we construct a model in this way, can we have an issue of super specialized model? I think this was happening at the very early part of this talk, where you were going through, selecting of the seed values and then iterating to form the clusters.
Correct. So if that's why it's important to look at a lot of the statistics and all of the qualities, right, of your model. So the things that you're working on, the techniques that you're using, right? You really want to make sure that you're using the best ones. K-means you end up with a very specialized model. If you say put K equals 100, right, and just let it rip, you will end up with 100 clusters. But the problem is then, yes, you're going to end up with a model that is so specialized that only a tiny fraction of your data really belongs to there, right? So yes, definitely that is a concern if you grow too much, the number of clusters you're looking for. So it really depends, again, on the volume of data you're looking at. I think there's a famous PRISM model for clustering the behavior of people, right, in marketing. I think that model was it 90 something? I don't remember right now. I can break it to the next session, but there were like 90 something types of people that they had identified, but that's a specific work, right, that was done. So yes, so the answer is yes, we have to be careful.
Okay. Is there a mandatory, is it mandatory to specify the number of iterations? Is there a default value that's used?
Yeah, so there is a default value, usually on the k-means and on the expectation maximization, they have a default value, so you don't need to specify them. You can just use whatever they have. I was just stressing them, right, just to show you that you can go wrong if you stress too much of those iterations, for example, right? That might not be what you might want.
Okay. Is there a restriction using OML for Pi compared to Python?
Restriction.
Perhaps the question is more of maybe functionality, overall functionality that's there. I mean, I can take a stab at this one. I mean, essentially, OML for Pi is providing you a set of functions that you can invoke on top of the proxy objects that we have that correspond to in-database tables, right? We call them OML data frames. And so you can use that overloaded functionality, which is not the full range of Python. It's in V1, it's a select set of functions that we're overloading. But you also have the Python API to the in-database algorithms. And then the embedded execution, which is another facet of OML for Pi. After that, it's AutoML, where we're providing the ability to automatically select the algorithm, the features, and then do automatic model tuning. So those are some of the, I guess, elements of OML for Pi compared to what you would get with the generic Python. A different question, though, is there a threshold for low versus high number of attributes?
I would say let's call it 50 attributes. The problem with more than 50 attributes on a k-means is that you're going to start having to compute a lot of stuff, and then that sensitivity of that kind of model is going to be complicated for you later on. I would prefer to use expectation maximization, for example, on something like that for sure.
Okay. Marcos, you mentioned clustering. The clustering model is sensitive to outliers, and k-means handles it by normalizing data. So this person wants to know how to handle outliers when you want to apply an O-cluster model.
So on the O-cluster, we're going to see more details on the next session. The O-cluster is using the SQL interface, so we're going to see more details on that, and I can bring those details on that session, on the next session for sure.
Okay. Is there a way to incorporate string variables and string similarity between them?
So the string, when you bring string data, what we're going to do is we're going to convert those any categorical variables, right, into zeros and ones. And then that's going to be part of the model. It's going to be not beautiful, but that's the only way there is to convert a categorical, and character variables, right, into numericals. Because the methods on clustering basically look at distance using numbers, right? So yes, you can definitely bring, you can run tokenization on a document and then try to use that. But there are probably better techniques for document similarity, for example, as well. Right?
Okay. If EM is giving a better result, why would someone choose k-means or O-cluster?
And that's a great question. So we normally use many different techniques when we're trying to look at some of these processes, because if your problem is simple enough to solve, then you probably might want to use the simplest model possible. It's the same reason why if you're analyzing data and you have a logistic regression, right, that can compute the probability of a customer leaving, right, on your churn model, and then you build an 8-layer, 1,000 neural network that does the same job, but the improvement in quality of that gigantic neural network against your logistic regression might be 1%. So at that point, it's something that you might ask yourself, right, whether it makes any sense for you to create such a complex model. So sometimes it's good for you to have these different techniques to look at things. But yeah, I mean, if you have only one, if you are short in time, I would go with the expectation maximization, which is definitely a more modern technique for sure.
Okay. There's another one. Can you please share any data frame, sizing, or performance constraints that OML can attempt to address with the OML proxy object data frame?
Sure. I mean, I don't think we have any specific thing that would make it uh, run badly, Mark. I think when we think about performance, right? We have been testing for the past few months some proxy object data frames that are on the 800 million records with some 50 attributes.
Mm-hmm.
So I don't think there's any limits in terms of saying, well, this thing is going to choke or die or not work.
Mm-hmm.
So our models, when you think about Oracle machine learning models, right, they were built for the large database ecosystem and to perform on larger data set sizes, right? So the examples I'm playing here are very small, but you can definitely run the same thing on a 100 million record data set. It's not going to be a problem.
Yeah.
So I think
Just
that's the comparison with the open source Python, for example, right?
Just to add to that, I think that we're leveraging Oracle database as a high performance compute engine, right? So you get the benefits of things like indexes on columns, database parallelism, query optimization, even partitioning. So those are things that all help the queries that sort of the operations that we perform on the OML proxy object data frames to perform quite well, and so we're really leveraging the database to its fullest. Also, the machine learning is occurring inside the database, right? So those algorithms are parallelized. I think one thing I would comment is that when you are building up transformations on an OML frame, what you end up with are a series of views, right? One on top of the other. And so one consideration that you may want to do at a certain point is before engaging in, say, model building, you may actually want to materialize the transformations that you've gone through at that point. Because if certain things are being computed incrementally, that will take time. And you will want to perhaps optimize your model building by having those computations already performed. So there's just another consideration.
Right. And I think the last one I see is how to measure cluster separation if you're using Oracle data mining PL SQL packages to build a model. And I can probably show that next time for sure. So it's we have those kind of features there as well.
Great. Okay, well, I think that brings us to a close for today's session. So thank you, everyone. Thank you, Marcos, for a very interesting and exciting session again. And we'll look forward to the next event, which is Clustering 102 in a few weeks.
Thanks a lot. Thank you, everyone.